Hi, everybody, and welcome to today's lecture. Today is on, a lot of people are not here right now, and I know typically this one is toward the middle of the semester. Still have about 2 weeks for the spring break, so hopefully that will give you a breather a little bit, okay? And again, it's been a month since we started this class, and we are in chapter 11 today. Chapter 11 talks about the atomic structure. This is basically quantum mechanics, really, the roots for it. And then the next 3 chapters are going to be combined into one chapter. They are solids, liquids, and gases, basically 3 phases of matter. We're going to treat them as just one topic, basically. And so this is how typically this class works, okay? So you should have the notes. I think the notes probably are not still available, but you should have access to them before class starts, okay? So let me share with you the screen. Again, this is chapter 11. It's about the atomic nature of matter. This is one of the things that evolved over time. So people in the old days, they thought that there were 4 elements of matter, and they gave them all kinds of theories about them and what makes matter and no matter. At the end, basically toward the picture that was emerging toward the end of the 19th century, basically in the 1800s and so on and so forth, that matter is actually made up of tiny particles. We call them atoms, and atom stands for the fact that it is the smallest indivisible component of matter. It turns out that that picture was not really 100% correct, because atoms themselves are made up of tinier particles still. Namely, the 3 main components are electrons, protons, and neutrons, okay? And we thought that those are the bottom rock thing where things really stand. So there is nothing more elementary than these elements. Then we started discovering more and more of this. And first of all, elementary particles themselves came in all kinds of things. So they have their n-type versions of them. For each electron, there is another electron that is like it, except that it has a positive charge. It has everything the same, namely the same mass, the same behavior, the same so-called spin, and the charge is numerically the same, except that instead of 1.602 times 10 to the negative 19 coulomb, it is positive, okay? Now, that positron is not stable, in a sense that, at least in this part of the universe, is not stable, because it immediately recombines when it finds another electron and basically vanish. They cancel one another in an annihilation process. Basically, they annihilate one another, so they go away completely. And they convert their masses into energy. So basically, they become extremely high frequency energies called gamma rays, okay? Same thing is true for the proton. The proton, there is a particle that is like it in terms of mass. The mass is identical, 1.67 times 10 to the negative 27 kilograms. And also the charge of 1.602 times 10 to the negative 19, except this charge, this electron is a negative charge, okay? So we call that the n-type proton. Again, it's not a stable particle. We make it in the laboratory at will, but then immediately it recombines when it finds another proton, and again goes into energy. So that is basically what's particles and n-type particles exist. So that picture was kind of held for a little longer until we started basically theorizing that maybe, hey, the proton and neutrons and all of these elementary particles are made up of tinier particles, because there are other particles that start to pop up, neutrinos and muons and kappa particles and so on and so forth. So there was a laundry list of particles at the end, just like, for example, with the atoms. We thought, okay, we have them all under control. We have, first of all, there were 4 elements, then we have now molecules, but then we found them divided into exactly a certain number, around 100 of them, okay, in nature they occur. But then those elements, basically in the periodic table, start to, they themselves become made up of stuff, which is 3, which is good. I mean, the smaller, the better. It seemed like we had a handle over it. Then those three started to basically multiply all over the place, okay? So it became ridiculous at some point. Then the standard model came up with actually a new description of those particles using the so-called quarks, okay? Now, quarks themselves, they seem to be the smallest amount basically of matter, except that this is not in the sense that you might think. And if you look at the mass of the proton, for example, it's not necessarily that of the sum of the three quarks that they make it. So there is energy involved. So now it's still an ongoing topic, basically, in elementary particle physics, trying to understand what's going on. So this is basically in a nutshell where we stand in terms of how matter is structured. So again, we're going to talk about the atomic hypothesis in here. So this stuff that seemed to be modern is actually a little bit outdated. In the early 20th century, yes, it was kind of revolutionary, but then we came now far from that point. So the characteristic of the atom, atomic imagery, how can you take a picture of an atom? When I was actually in high school, there was this people, and I think still an ongoing thing right now. If you go on YouTube, you'll find it actually too. They don't believe the atom exists because they say if we don't see it, it doesn't exist. That's their reasoning. And you try to argue with them at that time based on spectroscopic studies and based on basically analysis involving the collision with the charged particles that we know that they are positively charged, the so-called alpha particles. When Mr. Rutherford hit the foil of aluminum, not aluminum foil, they were actually gold foil and silver and different kinds of them, and he noticed that the only way for this one to exhibit this scattering behavior was the presence of a charged, positive charged inside, and then you still have the outside, which is in the negatively charged behavior. So that was also in a lot of experiments, Mr. Millikan was able to find the charge. So you explain to them what other people did, but they tell you what? We have never seen that. We have never seen it. So if we can't see it, it doesn't exist. I literally asked one of them, did you see your brain? Don't tell me that you saw a brain of an animal that is dead, or the one in the meat place that have brains. No. I mean, your brain, did you ever see it? If you never saw your own brain, do you think you have one? So again, in this case, you don't really need to see your brain. You can argue that basically based on your reasoning, based on your thinking, you have a thought process, and that somehow is related to something that is inside of you. There is a function, and you can go back into the research and actually what the butcher has and everything else to see the connection. And indeed, you do have a brain. So that's basically how you conclude that. So again, taking a picture of the atom is very hard, very, very hard. With light has a special wavelength that we know ranges anywhere between 700 to 400 nanometers. It's very, very short distances. A nanometer is 10 to the negative 9 meters. So think of a meter, which is this much, roughly. This is about a meter. Take this meter and you divide it by 100. So this is probably what a centimeter would look like. It's about this distance, okay? It's probably less than that. That's what a centimeter would look like. Take that centimeter and divide it by 10. It's like a piece of hair, basically. That is a millimeter. Take a millimeter and still divide it by 1,000. Can you imagine that? Take a piece of hair, the width of the hair, not the length, okay? And divide it by 1,000 smaller pieces. That is actually a micrometer. So that tiny piece that you can even see of the order of basically a microbe, which is really what the microbes stand for, a micro, an organism of the size of a micrometer. Take that and divide it by 1,000 further still. That is what a nanometer is. Albeit this is about 400 of that. This is the shortest wavelength, is about 400 nanometers. This is the blue light. If you want to see something, it has to have this light can resolve it for you. This distance between the light has to resolve it for you. Now, an atom is of the order of an angstrom, which is an order of 10 to the negative 10. So if this is like, this is about 100 times a nanometer, which is about what, 10 to the negative 7 meters. An atom is still 1,000 times smaller than the blue light, which is the shortest wavelength that we can see. So the wavelength will spread around it 1,000 times bigger. So it cannot really resolve the atom. That's why light cannot be used to look at the atoms. That's why you cannot use microscope, for example, and put an atom underneath and look at it, because there is no way your visible light, your eye, that really works with visible light, can resolve, can tell you the details, that's what resolve means, of the atom, because it uses this super huge distance, 1,000 times bigger than what an atom is supposed to be. So you can't do that. However, for big enough atoms, there is another technique we use, actually, and we were able to take pictures of that. I don't know where those guys from the high school are right now, but you can send them a picture. I'm sure they have seen it if they look for it out there. We use an electronic microscope to use electrons. Electrons have wave behavior. They behave like waves, okay? And if they are moving fast enough, their wavelength will be of this same order of an angstrom, okay? And they can resolve somewhat, not to a lot of detail, what the atom looked like. Looks fuzzy, but that's good enough. So the atoms do exist, and we were able to see them. Okay. Then, of course, the atomic structure. We're going to talk about the atoms and the fact that I already mentioned that they are made mainly out of three main components. They have the electrons. They have the protons and neutrons. The neutrons and the protons sit in the nucleus, and the electrons revolve around them, okay? Electrons and protons have opposite charges, so they are held to one another by an electrostatic charge, electrostatic force. So you're wondering what in the world is happening in an atom like helium, which is the next one that has two protons. Any atom other than hydrogen, yes, you can think about it that way. Hydrogen is fine. You have a proton and you have an electron, and both of them are held together by the electrostatic force, because this one is supposed to be moving super fast around it. So it's like the planet Earth revolving around the sun, more or less, like that model. Although that model fails miserably because of the fact that an electron moving will cause it to radiate energy. So this path is not really a stable path. So there is another physics at play, and that is quantum mechanics to explain what's going on in here. But if I go to the next atom after hydrogen, which is helium, then we have a problem big time. We have a proton, and we have a proton, and of course you have a neutral charge in here, a neutron and a neutron in here. But these two are next to one another. They're both of them positive. This should break apart big time if it were only due to electricity at those small distances of the order of a femtometer, of the order of 10 to the negative 15 meters, which is a lot smaller than this distance. This distance is about an angstrom, 10 to the negative 10 meters. So now you're looking at 100,000 smaller size than that, 10 to the negative 15. So at that point, you're looking at this distance, nuclear forces take over. Nuclear forces are a lot stronger than the repulsion between the charges. So it's going to actually hook the proton and the proton together. It's still, there is a repulsion. It's still not really a 100% stable, because there is a repulsion due to electricity. Just with the next agitation, there is a little bit of repulsion, but nuclear forces are stronger at that point. They are 100 times stronger than the repulsion, which is about 1 over 137, actually, to be more specific. So here comes the role of the neutrons. The neutrons, they have, yes, zero charge, so they don't repel one another. They don't repel anybody, as a matter of fact, positive or negative or no charge. But they have played the same play of nuclear forces. They too pull things together due to nuclear forces. So now, with the help of the neutrons, the electrons now they are glued together due to nuclear forces. And this is true for the next element, lithium, beryllium, and you go throughout the periodic table. So the more now protons come into play, the stronger the repulsion, the more neutrons are needed to keep things together. Initially, it's a one-to-one correspondence. For every proton you bring to the mix, you need to bring another neutron to the mix to help them stay together. Now, when the atoms become too big, actually you need more neutrons than protons. For every proton you bring, you need at least 1 to fraction of 1 more than that. So usually you end up with 2, 3, 4 neutrons at the end, more than the actual protons. This picture becomes a little bit problematic for the atoms that are super big, because at that point, the two ends of the atom, the two ends of the nucleus, I should say, one on this side and one on this side, they're too far away to be affecting one another through the nuclear forces, attracting one another through the nuclear forces. At that time, electrostatic forces, the fact that the charges repel, will play a major role and will not keep the nucleus stable, and then causes the atom to go back into a more stable configuration. That's why we really can't grow willy-nilly the number of protons and neutrons inside the nucleus, because even then the nucleus becomes unstable and you have reached a certain point. That's why the number of elements is around 100. In nature, around 90 actually, that occur naturally, except the ones we make in the lab. And those are not 100% stable because they immediately decay into something else, okay? So this is basically in a nutshell what's going on in here. Again, so this is basically in terms of what the periodic table, if you look at it, has nice features in it, okay? Periodic table that you find on every chemist's basically in every chemist's lab has on one side you have all of the periods, which is called periods in this case, okay? And then you have all of the groups on one side, okay? And there is a similar chemical behavior, because you will see that the number of the outer electrons, which is really the only player when it comes to chemistry, for the electrons, that determines the chemistry of the elements. So you have elements that start from one side and go all the way to the neutral elements on the periodic table. So basically, that is how the periodic table is organized. So there is a logic behind it, okay? In terms of chemical properties, and in terms of also physical properties too. So they are all determined by that. So that is the periodic table. And then we're going to check the size of the atoms. You will see as you move along in the same group, the size increases. As you move in the same period with increasing number of charges, number of basically protons, the size actually shrinks, okay? Because there is more positive charges, more basically protons inside, so they pull more on the electrons and make the atom look smaller than what it is, okay? Obviously, if you move this way, hydrogen atom, and then you start to go up and up and up, then you're going to have more and more elements in it, and the atom starts to grow. But then if you move along a certain line, the horizontal line, the size starts to become smaller and smaller and smaller and smaller. So that is the correspondence. Then we're going to talk about isotopes. Isotopes are elements basically that have the same number of protons, namely electrons, because electrons and protons have to match one another for the atom to be neutral. But they may have different number of neutrons, which means that their mass is different, because the mass depends on how many particles you have in the nucleus, because the electrons are so tiny. The electron's mass is about 9 times 10 to the negative 31 kilogram. It's so tiny compared to the mass of the proton or that of the electron, the neutron, which is about 1.67 times 10 to the negative 27. This is about kilogram also, about 1,000 times bigger, actually 1,900 and something bigger. So in this sense, most of the mass of the atom is actually inside the nucleus. So now you have an isotope which has the same number of protons. Both of them have the same number of protons. Two isotopes, both of them have the same number of protons, but one of them has more neutrons than the other. So in terms of their chemistry, they're identical. Both of them do the same thing. Both of them do the same, they form the same chemical compounds. Both of them have the same colors in terms of their physical properties. They have the same strength. They have the same everything. Okay? So they look identical, except the mass is different. So their inertia is different. And this can be useful in some stuff, okay? Some places where you want to do things. For example, you have two well-known isotopes of uranium. One of them is more reactive than the other. One of them is can easily, basically, is not stable in a sense, so you can easily break it down and get energy out of it. Uranium-235, that's an isotope, versus uranium-238, which is a different isotope, which is more stable than the first one. Again, this is basically how you, if you want to build a nuclear bomb or nuclear reactor using uranium, you have to get uranium-235, which doesn't occur in nature that much because it decays more rapidly than uranium-238. So you'll have a lot of uranium-238. So you have to enrich your sample to make it more potent. So that is basically stuff that has to do with the properties of the isotopes. Some isotopes, they are very, very useful. For example, carbon-14 dating is used to date things in anthropology and things like that, because of the fact that we know that a plant, for example, produces a certain amount of that, but then when the plant dies and starts to become inactive, then at that point, it ceases making it, so at that point, all of the carbon decays naturally. So you know how much the decay of the carbon is. So in this case, you can tell the age of that one if you just find the proportions of how much of this one versus the other one. Then you know how old the sample is. So it's very interesting stuff. And then we're going to talk about compounds and mixtures. Compounds and mixtures is basically compound is like, for example, you make like H2O molecules that have all kinds of similar structures, but mixture, like, for example, the air, okay? The air is a mixture between mainly oxygen and nitrogen, okay? Molecules, and then we're going to talk about antimatter, which I already mentioned briefly, the fact that for an electron, there is an anti-electron, and for a proton, there is an anti-proton that you can make in the lab. And then there is this strange thing, okay? Dark matter. Don't confuse it with antimatter. Antimatter, we know what it is. It's made out of regular matter that we know and work with in the laboratory, and we can see, we can interact with it, emits light and does everything that we know about. The only thing, it's not stable because of the fact that we live in a part of the universe where it's dominated by regular matter. So antimatter and regular matter cancel one another, and at the end, we will have basically energy. But dark matter, though, on the other hand, is another problem. Dark matter exists because we know it exists. What is dark matter? We don't know what it is. At this point, we don't know what it is. We have suspicion of some stuff that maybe that's what dark matter is, but we don't know what it is. Not only it exists, but it exists with tremendous abundance. It dominates the form of matter in the universe. If you are in a room right now, wherever you are sitting, actually your room where you are, it's too crowded with it. Actually, if you were to see it, you cannot see far because of the way that dark matter is piling up basically wherever you are, okay? If you can interact with it, if you can somehow touch it, you cannot budge from your place because it's surrounding you so much. But we don't see it, we don't interact with it. We run our hand through it and it goes straight through like a hot knife on butter, basically. And it is something, basically the word dark in this case is because we don't know, it's a mystery, that's what it is. But we know it exists. We know it exists, and it exists with a lot of it. How do we know it exists? Because of gravity. That's why we know it exists. The force of gravity, it works with it. But the electrons does not work with it, does not interact with electricity and magnetism. That's why we cannot see it, we cannot touch it, we cannot smell it, we cannot feel it while we're going through it or while it's going through us. Basically, that is really why We don't do that. It doesn't also interact with nuclear forces, because if it does, it will interact with any of the particles that we have, like in our bodies and everywhere, same thing. So it only interacts with gravity, and because we can detect gravity, we can know it's there. And it's not just we know it's there with a lot, huge amount, okay? So that is basically the last part in here, okay? The dark matter. So if you are made out of dark matter and sitting in here and listening to this class, you know probably how it feels, that we are the missing part of it, okay? But if you are made out of regular matter and you're sitting in this class, think of everything else that is happening around you and that you have no knowledge about it, okay? You have no control over it, okay? So this is, by the way, if you looked at my picture on Zoom, when you log in, and I'm not basically on, I don't have my camera on, you see a picture of this guy, Richard Feynman, because I really like the way he was teaching physics and the way he approached physics, and he's one of the best physicists out there that ever existed. He passed away a long time ago, around 20 years, 30 years ago, actually. And he was actually a Nobel Prize winner too, and he did so many things in physics, unbelievable. So one of the things he said, that all things are made out of atoms, little particles that move around in perpetual motion, they never stop, attracting each other when they are a little distance apart, but repelling one another when you squeeze them to one another too close. This is the model basically for the next 3 chapters. You have an atom in here and an atom in here. They get too close from one another, they pull one another. Try to make them even closer, they repel one another. Okay, so that is basically what's going on in this case. That's how you understand then solids, and you understand liquids, and you understand gases later on, okay? So, but for molecules, there is an attraction between different atoms. For example, if you look at water, it's made out of an oxygen atom and a hydrogen atom and another hydrogen atom in this configuration. So this is H2O, so they are stable. Try to put the H closer to the O and it will not work, okay? So the first thought of Aristotle to be a combination of 4 elements. These are the elements: earth, air, fire, and water. If you have seen an old movie with Bruce Willis, and I forgot the other actors in it, it's called The Fifth Element, okay? In that movie, they added actually love as a 5th element to make basically whatever things in there. So it's still popular in the current culture. So this idea that the 4 elements are the main things that makes, actually the title of the movie is The Fifth Element, okay? And so they had the earth, they had actually air, and they had fire, and they had water. And that is how they thought the 4 elements of, that everything is made up of, okay? And thought to be composed of atoms by Greeks from the 5th century. There was this hypothesis a long time ago that if you take substance and you start dividing it, basically take a piece of dirt, I mean a rock, for example, break it into 2, just smash it on the floor, take that, any piece, smash it on the floor or smash it by a hammer, and continue doing that. Ultimately, you'll reach a point where there is no more divisions to it, and that is what the atom was, okay? That is basically how the atom was divided. Of course, it's a thought experiment, but that does not answer the question of what is the atom, on how to basically work with it, or how it's made, or things like that. The first idea that came actually explored later on is by John Dalton, when he was experimenting actually with the gases and things like that, and noticed that there is a certain proportion for certain gases. If we bring certain volume of it, the mass is so much. If we double the volume, the mass is, yeah, it has to do with the density, but then if you change the temperature, this number also changes the number of moles and gases, and there is this ratio that seems to be continuous, indicating that there is some inner structure inside made up of a huge number that later on measured the Avogadro's number of them per mole. So that is basically in a nutshell how this one was. Robert Brown, a botanist, observed collision between visible particles and visible atoms later formed by confirmed by Einstein as evidence for the existence of the atoms. So basically, the Brownian motion is, if you take, for example, oil, okay, or any fluid, okay, and you put dirt in it, you will see that the dirt will have this motion that is basically kind of random, jiggly motion, left and right, and so on and so forth. So what the theory was then is that somehow this piece of dirt is colliding with the internal structure of these atoms. Later on, after Mr. Max Planck came up with his theory for the black body radiation, Mr. Einstein borrowed that idea from him basically and applied it to this model of the Brownian motion, and he explained it. And that resided on the hypothesis that the atoms are made up. I mean, matter is made up of smaller particles that we don't see, and that's what causes these things in here. So it's like, for example, you are on if you can think of a huge beach ball, okay, big beach ball, and there are a bunch of people kicking it around on the beach, for example, and you go very high in the sky, on a plane, for example, where you can't see the people. But since the ball is huge, you see the ball basically going in a random fashion because people are kicking it around. That's exactly how the interpretation for the Brownian motion, those people being the atoms, and that is the beach ball is being the basically the pieces of dirt or the droplets that you have in it. And that is how you can find that is how basically we became more and more aware of its existence, okay? Again, it's incredibly tiny. I already gave you the scale of which. Take a piece of hair, which is very, very small, and divided by 1,000, it's still 10,000 times bigger than what an atom is. So the piece of hair divided by 1,000 still. So the piece of hair basically is about what? 10 million times wider than what the atom is. So that is basically roughly the size of the atom. And it's still, we're not talking about the nucleus. The nucleus is even smaller than that, okay? So the distance between the nucleus and the electron, for example, and the hydrogen atom, this distance, which is of the order of 10 to the negative 10 meters, this radius is 10 to the negative 15. So if we happen to live on the planet Proton, if you have a creature that can live in here, the electron is so far away, actually. It's unbelievable. It's incomparable to even to the solar system. So it's made up of mainly empty space for all practical purposes. There is nothing in it. With the exception of those two sizes, there is nothing. It's mainly empty space because 10,000 times when you find the first electron, that is really far away, okay? To just give you an idea, for example, with the Earth and the Sun, the Earth, the Sun has a radius of about 700,000 kilometers. Or maybe the diameter is twice as much, which is about 140,000 kilometers in radius, okay? The Earth is about 150 million kilometers. So if you can stand the sun, of course, if you can sit on the proton, which is impossible because it's too tiny, so you need a tiny particle in there. So if you can have that same vision in here from the perspective of the sun, and you look upward, it's only about 1,000 times. And you see the Earth. Whereas in here, it's 10,000 times, it's 10 further away. So it's really, really far, okay? To look, for example, onto Mercury, which is somewhere in here, it's even less. It's only a few hundred times further. So again, this is even wider than the solar system. So if you were to compare, and of course the comparison is wrong, so don't push too far. If you were to compare the size of the atom to the solar system is actually has more crowded stuff in it than what the atom is. The atom is far more emptier than the solar system. It's mainly made out of empty space, nothing. Isn't that amazing? That you and I, that are made of so many huge number of those, which are so tiny, but they are mainly empty. Okay, there is empty space in there. So numerous, of course, you have a huge number of them. If you take a mole, for example, of a gas, you need to have about 10 to the power 23. That is 1 followed by 23 zeros. I don't even know how to say that number, okay? Of them in 1 mole. So it's really a huge number, okay? And they need to be in perpetual motion. They can never stop, okay? They can never stop. So even with lower temperatures, the atom is still moving. Even at 0 Kelvin, the atom is still moving. So they can never stop, okay? And they have existed ever since the universe basically was created. I lied a little about that, okay? The atoms formed around 380,000 years after the universe came to be, basically after the universe, after the Big Bang. The reason why we say that is the following. Immediately after the Big Bang, the temperature was so hot that not even this atom can exist. It only existed when the universe cooled just enough for it to become visible, and that is when the first atoms start to form, which is obviously the first ones are hydrogen, and then of course whatever combinations left for helium. So those are the primordial basically atoms. Then after that, the rest of the atoms in the periodic table were formed by the stars, either during their normal life cycle or later on when they go supernova. So that is basically how this process went. Okay. We need to get, so again, I talked about how to take pictures of it. So too small to be seen with visible light, even with the shortest wavelength, which is the blue or even the violet, cannot decipher, cannot decode, cannot resolve. So light too long to resolve atoms. Okay. This is the item that I want you to remember, okay? So that if somebody, like I was in middle school, I'm in high school, somebody asked me, you cannot see it. Yeah, you can see it because it's smaller than the shortest wavelength that you can see with. Make sense? This is the item 1. Yes?
Yeah.
Okay, very good. So the atom, the light is too long, even with the shortest wavelength, it's too long still to resolve the atoms. That's why we cannot see it with our eyes, even on a big microscope, a regular microscope. However, an electronic microscope can take good pictures of it. Okay, you cannot see it because it's still not visible, but you can take pictures with it. So a change of individual thorium atoms in 1970 electron micrograph image. So this is basically what an electron microscope revealed as ripples and rings by scanning, tunneling, and microscope in the mid-1980s. Classical models has a nucleus at the center surrounded by electrons. Okay. Let me tell you something also. This is not real. This is not how the atom look like. This is just a model. Okay. So that's just a model. So this like orbits, and you have this thing's going. No, when you are at that level, no, this is not true. You can't really find where the electron is. There is a cloud, if you will. There's a probability of it being in here, but not exactly there. Okay. So this is just a model, not a real picture. Does everybody understand that?
Yeah.
Okay, very good. So this is item 1 for today. So again, atomic structure, there's a nucleus in the center. That's where most of the mass is. And then you have, of course, it's made up of nucleons, and nucleons are building blocks of the nucleus, which are mainly basically protons and neutrons, okay? And all are identical in a neutral state, a neutron. So a neutron has no charge, a proton has a positive charge, and positive charges repel positive charges and attract negative charges. And nucleons, namely the protons and neutrons, they're made up of quarks. If you look at a proton, this is again a model, not a real thing, okay? It's made up of 3 quarks in here, okay? I think 2 up, quarks and one down quark, and the word up and down are just basically just naming, okay? Just like, for example, when we said that the electron is negatively charged and proton is positively charged, just by convention, okay? Same thing in here. We ran out of names, so we started giving names, okay? Up quark, down quark, charm quark, and all kinds of other names, strange quark. So it doesn't mean anything, those words. It's just basically we're trying to distinguish between their different properties, because each quark has its own charge, has its own mass, has its own properties. And those are the ones that basically determine all of the properties of the entire particle, in this case a proton. Again, this is a model. You will find that these protons need to be, these quarks need to be held together. And what holds them together is actually another particle called the gluon. Okay? Gluon has zero mass, just like the photon, like particles of light. But they carry with them, they hold together. Those are the ones responsible for nuclear energy between these quarks in here, inside the proton, okay? There's tremendous amount of energy, so that you cannot really break a proton easily. It takes tremendous amount of energy to really have it spilling into gas, basically bring another proton, smash them against one another to see what's inside of them. And even that is not stable, because immediately whatever comes out recombines and give you other particles, okay? So there are tremendous amount of energy in there. Okay. So again, the elements refer to the particles that make up a substance. This is what the atoms are. Element substance composed of only one kind of atom. So that is basically one kind. To date, about 115 are known. 90 occur in nature by themselves, and the rest they're made in the laboratory. Okay. The words atom and elements, sometimes we use them exchangeably. Okay, so when we refer to an element, we are really looking at them. So composition of living things, they're made up mainly of these elements, okay, or these atoms: oxygen, carbon, hydrogen, nitrogen, and calcium. So those are what make up mainly the living organisms, okay, or living matter. So it's made up of this 5 elements for the most part, okay. Obviously, you're saying, okay, how about sodium? We need sodium. Potassium, we need potassium. Yes, we do. But these are the makeup of the living organism for the main part, okay? So a chart chemist showed map of elements arranged by atomic number, classified by the number of protons in the nucleus. So basically, as the number of protons increase, you have you move along the periodic table. Arranged from left to right, each one more proton and an electron than the preceding element. On the far right, outer shell are filled to capacity, known as noble gases. So here is the periodic table. These are the noble gases: helium, neon, argon, krypton, xenon, and radon only. Okay, there are, what, 6 of them? And they're called noble gases or inert gases because they don't participate in anything. Their electrons at the outer shell, they're full. You cannot remove an electron. You cannot add an electron in a regular chemical reaction. Okay, you can ionize them, and sometimes they come ionized by themselves, basically with no electrons. Like, for example, the case of helium. Helium in some natural processes, for example, in radioactive materials like polonium, for example, will give you hydrogen atom with no electrons in it. That is actually called the alpha particle. And then later on, when it finds electron, grabs into them and becomes helium again. And then you have the hydrogen group in here. So this is basically this is how you think about it. On this side, you have 1. This is the period 1, period 2, period 3, and so on and so forth as you come down. The groups are coming down in here. Most of the times, they are named after the first element. So you have the hydrogen group, which is, or the lithium group, actually, because that's actually more representative of this group. Then you have the beryllium group, the scandium group, what is scandium group, and then you have titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, and then you go to boron, carbon, nitrogen, which has a different name, oxygen also, which has a different name, and halogens, which is actually the fluorine group in here. Okay, so this is basically the different groups, and again, these are the noble gases, or the helium group, or neon group, helium, neon, no, neon argon group. I think that's how they refer to them in chemistry. It's still, their atoms, they're basically, they're full. And here, they can accept one electron, this one's. If they accept one electron, they become negatively charged. These guys, they can give one electron. And if they give one electron, they become positively charged. Like, for example, if I take sodium in here and chlorine, chlorine can take one electron because it's short one electron to become an argon, okay? Just like the argon. Sodium, on the other hand, has one more electron than what the neon does, okay? But it's neutral. It has one electron, more electron, but it also has one more proton. So this sodium atom by itself is neutral, but it's highly reactive. In a sense, it can give easily its electron. On the other hand, chlorine is one electron shy of being full like the argon, but also it's one proton shy, so it's neutral, but it's also highly reactive. It can easily take another electron to become stable, okay? To become basically neutral. To become full, I mean, I don't mean neutral, to become full in the outer shell. So in this case, what happened when these two meet, this gives an electron, this receives an electron. And now you have two ions. This ion, which is positively charged, short one electron. So the protons are more one than the electrons. This is actually is also ionized. It's a negative ion. So in this case, what happened is, because it has one more electron than its protons, so when the two, they are next to one another, they attract one another and they become stable in what is known as salt. So this is how salt is formed, okay? And this is typical for a lot of bonding in here in chemistry, where some will give an electron, others will receive that electron. Now, in some situations, this is not possible, okay? What happened in that situation is that there is a sharing of the electrons. Nobody gives, nobody takes, they share it, okay? Like, for example, take the water, the oxygen, which can accept two electrons. Remember, this place in here can accept two. This place can accept three. This place can accept four. And then we become into a gray area in here, what's going on. So this can accept two to become like a neon. Its outer shell is full. So what it does in this case, it goes to a hydrogen and grabs one from it, but it still needs another one. It goes to another hydrogen atom and grabs another one of it, but they don't really go completely to the oxygen. They stay somewhat in the middle. So this binding is slightly different than the first one. So this is called the ionic binding. And then there is covalent bonding, basically, where they share electrons. Albeit in this situation of the case of the water, the electrons are slightly closer to the oxygen than the middle, which makes this molecule of water actually a little bit polarized. Now, you have, what do you mean that polarized? Is slightly electrical charge on one side versus the other. So it has, it looks like it's, on one side it's negative, on the other side it's positive. So water molecule with another water molecule, now they can do another kind of bonding, because one of them is slightly positive on one end and the other one is slightly negative to the other end, so they come closer to one another. So this is another kind of bonding, okay? So there are all kinds of bonding. There are 4 of them, okay? So we'll get into that probably sometime in the future. But again, this stuff you probably have learned it, or you will learn it in chemistry somewhere, okay? Again, we talked about the relative size of the diameter of the outer shell are determined by the amount of electrical charge in the nucleus, gradually decrease from left to right across the periodic table. As nuclear charge increases and the electrons are added to the inner orbit shrinks. So here is basically what's going on. Obviously, the hydrogen atom, you have an electron and a proton. The helium in here, you have 2 protons pulling on each of the 2 electrons, so it's slightly smaller. And as you go here from lithium and beryllium, again, you have more and more protons pulling on more and more electrons. Electrons are lighter anyway, so they're going to bring them closer and closer until the size becomes smaller. So in this size, the sizes are becoming smaller. Obviously, in here, we're increasing because we have more stuff now. We have more shells to fill now, okay? Initially, we only are worried about the first shell, but then you have to go to the next shell. That's why the size of lithium is bigger than hydrogen, and sodium is higher than lithium and so on. What is it? What is this one? Potassium is higher than sodium and so on and so forth, okay? So that is how the periodic table works. Make sense? Yes?
Yeah, it
Yes.
does.
Okay, very good. So an ion is a charged atom. I already talked about the fact that what happened to chlorine and sodium, okay? So positive ions has deficiency of electrons, like for example, sodium. Sodium, when it loses its electron, becomes positively charged because now there are more protons inside than the electrons, because they used to be even until one of them left. Then in this case, the protons are more, okay? So in this case, it's positively charged. Negative ions has an excess of electrons, like the case of chlorine. It was neutral before it borrowed an electron from sodium. So now it has more electrons than protons, so it becomes negatively charged. Isotopes are atoms of the same element with different numbers of neutrons. So in this case, they have the same chemical behavior, identical chemical behavior. This is not correct, okay? So it has to be chemical behavior. But physical properties, they depend also on the mass too. So if they have different masses, they will have different physical properties. So in here, behavior, what I mean by it is chemical behavior, not anything else. So protons in nucleus matches the number of electrons around the nucleus, but not necessarily the number of neutrons. So neutrons have no charge. So you can have as many as you need, as long as you need them, okay? Because if you have too many of them, also they can cause things to become unstable. So not based on electrostatic forces, though, based on other forces. So isotopes, atoms of the same element with different number of neutrons, identical behavior. Again, why is this chemical behavior? Okay, identified by their mass number, total number of protons and neutrons in the periodic table. So if you go back into the periodic table, usually they give you the numbers in here. If you look very closely in here, it's 1.0079, okay? That is the mass of the hydrogen atom, which is really one proton for all practical purposes. And here you have 4 of them. Why you have 4 of them? You have 2 protons, but you have also 2 neutrons. So it becomes 4. If you look at this number, it's 6.9 or 7 actually, okay? Again, you have 3 protons, but you have 4 neutrons in here. So for a total of 7. So the mass, there is a little bit of an issue there of why it's not exactly 7, and that is because each one of them has its own, they contribute a little bit to the bonding, and that's something else that we will see later on when we get into relativity, and that is where the nuclear force is coming from, actually, okay? Again, beryllium, you have 9. So in this case, you have 4 protons and 5 neutrons. So the number starts to differ now from this point on. You have 11 in here. You have 12 for the case of carbon, which is 6 protons and 6 neutrons, okay? Nitrogen, again, you have different isotopes for this too. So there is also isotopes where have more protons than this one, than 6. Nitrogen, you have 14, 7 and 7. Oxygen, you have 16, 8 and 8, okay? Fluorine, you have 19, which is 9 and 10, yes, okay? And in here you have 20, okay? 20, which is what? 11 and 9, I guess, okay? No, 10, I'm sorry, 10 protons. What am I talking about, okay? 10 protons, because this number, the up there and in here, is telling you exactly how many protons you have. So this is 10 and 10, 9 and 9, I guess. No, 9 and 10, 8 and 8, 7 and 7, 6 and 6, 5 and 6, and then you have here 4 and 5, and 3 and 4, okay? So again, you just subtract this number, 11 from 23, so that gives you 12 for sodium. If you look down in here, let's say, for example, take anything in here, it doesn't matter. What is this one? Rhodium, it has 45 protons, and it has overall 103. Obviously, 45 plus 45 is 90. So there is a difference of 13 in addition to that. So there is more 13 protons than, so you have 45 protons and 45 neutrons, plus 13 neutrons. So you have what, 58 neutrons to keep this guy stable. So as you move along in here, the number of neutrons start to become bigger and bigger. They start almost even. Like in this case, you have 2 and 2. Or in this case, you have 8 and 8, okay? Or in this case, you have 10 and 10, okay? Or in this case, you have 7 and 7. There are some imbalances already here, okay? Like, for example, 5 and 6. But as you move along, the numbers start to differ big time, okay? You need more neutrons to keep that many protons basically from separating until at some point in here, you become in places where they are not completely stable in nature. You have to make them in a lab and they don't become stable. That's why the number of new elements in the periodic number table is limited. It's because of that. You don't have enough neutrons, and even if you bring more, it's not going to keep them from flying away. Okay. So identified by their mass, which is the total. So basically, I hope you guys can, if you see a periodic table now, you can identify what these numbers are, okay? One of them is called Z, which is the atomic number, and the other one is the atomic mass, which is this one, which is the sum of these two, okay? The atomic number of an element matches the number of the protons in the nucleus and the electrons in the neutral atom, or both of the above. Of course, it's both. Again, this is the atomic number. Atomic number is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That is what the atomic number is. The atomic number for this element, what is this one? Hassium, it's 108, okay? Its atomic mass is 269 in this case, okay? So a nucleus with an atomic number of 44 and a mass number of 100 must have how many neutrons? I have 44 protons. That's what the atomic number is. Or 44 electrons, whichever you want to call it when it's neutral. But I know its atomic mass is 100. So how many neutrons would you need to make this 100?
56.
Absolutely, because 56 plus 44 add up to exactly 100, okay? When an atoms of different elements bond to one another, they make a compound, okay? A compound is different from the element from which it is made. It can only be separated into its constituents by chemical means. So salt, for example, is a compound because you have sodium and chlorine. They become basically one compound, one element together. It's like a molecule in this case. Substance that is mixed together without chemically bonding is called a mixture. You just put stuff together, okay? So like salt, for example, inside a water, that is actually a mixture, also it's a solution in that case, but it's still a mixture, okay? Not chemical bond. So molecules, two or more atoms bond together. For example, I have here the oxygen in the air is O2. This is ammonia, which is really prevalent in the outer planets, the gas giants. So NH3, and then you have in here methane, CH4, and you have the water molecule I was talking about earlier between the oxygen and the two hydrogen atoms. So those are typical molecules that you see them around you. So this one, in addition to the nitrogen make up the air. Most of the air that you're breathing and surrounding you is made up of mainly oxygen, which you're breathing actually, and the nitrogen, which is around you, okay? Ammonia also exists in the earth, but not with a lot of abundance. Methane is what you do when you cook on your with the gas, basically. And this is water, which is prevalent everywhere in here on Earth. Chemical reaction is a process in which atoms rearrange to form molecules. So basically, the bonding is broken between two different molecules and rearranged with another one, or added, or there was no bonding, now you have new bonding or something else. Pulling molecules apart requires energy. During photosynthesis, sunlight energy breaks bonds of CO2 to produce O2 and carbon, okay? So that is basically what the chemical reactions are. Combining atoms releases energy. Oxygen atoms combine with iron atoms to form rust, okay? So this is a chemical reaction, actually. I talked about antimatter. Antimatter is really the opposite of matter in terms of charges mainly. So antimatter, for example, if you want to form an anti-molecule, it will have the nucleus negatively charged, namely the protons are negatively charged and the electrons are positively charged. The opposite of an electron is called a positron. But the opposite of a proton is called just an antiproton, okay? And they can combine with one another to cancel each other, okay? So antimatter, if it exists in this universe, it must exist in a different region of this universe, because if it meets matter, they basically will cancel each other and goes into gamma rays, basically, which is super high energy electromagnetic waves, like light, basically, okay? So positrons have the same mass of an electron, but are positively charged. This was one of the things that was a hypothesis until it was confirmed in a laboratory. It was a major thing. I had a chance to go with my students, actually, when I was in St. Louis to an underground facility. It's not there really, it's up and ground too. So we went both up and down, where they actually make antimatter. It's in the Fermi Lab in Chicago. And basically we saw how they use, at least in the past, used to work with the antimatter. Now they don't, they focus mainly on neutrinos. But that's basically part of the process that you do in the laboratory. That's how we know they exist, actually, they practice. So you can make them and you can watch them through their trajectories. They have the same mass of the electron. I mean, yes, the same mass of the electron. But if you put them in a magnetic field, instead of spiraling this way, they spiral in the opposite direction. So you know exactly they exist and you know their properties exactly. Antiprotons have the same mass as protons, but are negatively charged. This too, they can be mad, but these things are only in the laboratory right now. So we know they exist just like the other elements, and there's no problem with that. Now, as opposed to dark matter, it's unseen and undefined matter, very different from the elements that comprise about 23% of matter in the universe, is an anti-gravity. So with the dark energy, which is 73%, and this guy, which is 23%, both of them are completely unknown, okay? They combine to make 96% of the universe. We, on the other hand, regular energy, all of the energy in the universe that is made up, that we deal with on a regular basis. And our masses, not just you and I, but the planet Earth, the sun, Jupiter, all the other stars, the entire basically known stars in the galaxy, all of them, including the black holes that we have, the neutron stars and everything in the universe, amount to about 4% of everything else. So we are 4%. They, on the other hand, the dark energy and dark matter is 96% of everything else in the universe. How did we know that? How did we come to this knowledge? It was actually Vera Rubin, she was studying basically the speed of the stars around the galaxy, how fast they move. If you take, for example, the case of the sun, okay, this is the radius of the sun. Imagine for a second that you can move around its center while you are inside, which is impossible. The theory expects that the speed will go linear as you move, because there is more and more mass that's going to pull you. But as you are further away, your speed slows down. For example, Mercury is here. Its speed is higher than Venus, which is here, higher than the speed of the Earth than in here. A year on Mercury, for example, Mercury does 3 times the sun before we only go once. Venus does almost twice before we go once. The Earth goes once around the sun. Mars, which is further away, will take even longer, almost 2 years for our year, okay? 12 years for Jupiter, 12 years on Earth for a Jupiter year on it. So the speed drops and drops like this. So this is basically how the theory predicts it. It drops like this. But what Vera Rubin had noticed is the stars, if you move away from the center of the galaxy, they start to behave more or less like this, because you encounter more and more matter, and obviously more and more dark matter too as you move along. Until you hit the edge of the galaxy, you notice that, hey, it drops a little, but then it stays steady. So now there are no more stars to account for this behavior. So there must be another kind of matter that we can't see, we can't account for, but it's out there, and it's out there with abundance. Combined with the dark energy that is responsible for the expansion of the universe, we account for nothing. basically the entire matter and energy that we have in the universe, to just add up to see how much it adds up, to see if we can find the mass of the universe, we find that it amounts to roughly about 4% of everything out there. So this is, again, the theory behind it. So this is all kinds of things. So this cannot be made of regular protons, neutrons, and electrons. That is basically the moral of the story. It's made up of a matter that has mass for sure. So it has mass. Otherwise, this behavior would not be noticed due to gravity. So how did we know that? Gravity, okay? So it has mass because it does gravity. In fact, it impacts the motion of the stars around the center of the galaxy. The stars are moving too fast for what they need to be. They need to be slowing down, but they are not, okay? Because there is more and more matter around the galaxy. And this was true for all galaxies, by the way, not just our own galaxy. So she started actually, Andromeda started studying other galaxies. So that we know for a fact that this object, this behavior is true for them. And it does not, though, have electrons, because if it's made up of electrons, we will be able to see it. It's going to interact with the electromagnetic radiation. We'll be able to see it, and we're going to the electric spectrograph, basically. It's spectrum, and we're going to see it and see all of the frequencies it reflects and attracts. So it's not made up of electrons. It cannot also be made up of protons for the same reasons, or neutrons, or any of the others. Other than the fact that it has mass, we don't know what it is, okay? And we can estimate its amount for sure, okay? So that is where we are right now. Physicists all around are working very hard trying to understand what it is made up of, and trying to see. They have some candidates for it, including neutrinos, by the way, but it's still an ongoing topic of the debate among scientists trying to resolve this issue. Okay. So this is the entire chapter. I was going to combine at least chapter 12 in here, but I thought that maybe we should really refrain from doing that. We are going, because chapter 12 and 13 and 14, they're actually the same idea, so I combined those together. And that's it. That's all there is in this chapter. Any questions before I stop recording related to this topic? No? So let's stop this one.